Welcome to the South Seas ABE room, where Nick Kralevich is going to present a talk about the art of defense, how vulnerabilities help shape security features and mitigations in Android. Before we begin, a couple quick announcements. The Business Hall in Bayside AB continues to host our vendor area. That is open until 5 o'clock this evening. Black Hat Arsenal also continues today in the Palm Foyer on level 3, and that runs until, I believe, 5 as well, but then there's also an Arsenal reception at 5 o'clock this evening. And also, if you haven't picked up any merchandise today, today is the last day to visit the Black Hat store for all kinds of great swags and books and stuff like that. Before we begin, make sure that you've got any phones and such on vibrate so we don't interrupt the talk. Thank you.
All right, good morning. Can everybody hear me? Yep. All right. Anyway, I wanted to say welcome. Thank you for coming today. I wanted to first of all say thank you to Black Hat. It's actually my first time presenting here, so I really appreciate the honor and the opportunity. Yay, yay, thank you. This makes me feel much better, so thank you very much. My name is Nick Kralevich. I'm one of the original founding members of the Android security team. I've been working in the security industry for about 14 years now, 7 of those years focused exclusively on improving the security of Android itself. It's been an amazing opportunity. I've had a really incredibly unique opportunity to basically watch Android sort of grow up and mature from a security perspective. I don't know, I keep hearing numbers, I don't know what the exact number is, but I keep hearing numbers like there's 1.5 billion Android devices or 1.75 billion Android devices, I lose track. But I'm pretty proud to say that I have code running on pretty much every one of them. So if you have a Eclair or Donut device, this is really the wrong place for it. So in my 7 years in Android, I've seen a lot of security vulnerabilities. I've seen a lot of bugs, and a lot of fear, uncertainty, and doubt. It seems like often you read in the press that some billion Android devices are affected by bug X. But after the press dies down, you never really hear what happens next. You never really hear about the lessons that we've learned and the improvements that we made to make Android safer for everybody. Today I'm hoping to give you a really small glimpse into how we think about security vulnerabilities and what we do not only to fix the bug, which is very important, but also to prevent similar bugs and make Android more secure for everybody. So what's our agenda for today? The first thing I want to do is give you a really quick overview of the Android security architecture. The architecture itself is something where I can spend an entire presentation on. We're going to talk about from a very high level and sort of the design and philosophy that we have behind the security architecture. After that, I'm really going to jump into some bugs that we've seen in the past and some vulnerabilities that we've seen in the past and talk about how Android responded to those bugs and what we did to make things better. At the end of it, I'm just going to give a little bit of my opinion, my advice about where we, Android, and the security industry as a whole, the entire ecosystem, go to make users safer, to protect data, to make sure that vulnerabilities aren't happening. But first, a word from our sponsors. So I head up the Android platform security team. And we really have 3 main goals in the team. Data at rest protection, data in transit protection, and then device integrity. But there's actually a lot more to Android than the code that runs on the device. Android is making really heavy investments to protect our ecosystem and to protect the entire ecosystem. Not just code which happens to run on the device. I'm really excited about the code that runs on the device. That's where my expertise is. But there's a lot of things that we're doing. First of all, when people think about Android security, this is the typical model that they think of. So first you have Google Play. We know that Google Play is the safest source to get Android applications. We have the lowest malware rates anywhere. But we also allow, in the interest of openness, we allow people to download applications from other sources. But we make sure we notify people that, hey, this is sort of risky. Do you want to do this or you don't want to do this? You have to get an install confirmation for every application, so that's a sort of additional barrier. If you've consented, we'll make sure that we're keeping track of the apps that you install and try to keep badness as far away from your device as possible. So we have our verify apps warning. Then we get to the stuff that I really love, the runtime security checks, the sandboxes, the permissions, all the stuff that makes Android Android. So this is actually a very simple model, but there's actually quite a few moving parts. And I don't expect everybody to, hopefully you'll get a copy of these slides later. This is a lot of information. But for example, we really focus on defense in depth. And I've already talked about Google Play. Google Play does a number of things to protect users, keep badness away from users. Static analysis, dynamic analysis. We're looking at applications to make sure that, are they trying to do something bad to your device? But we also get additional information, such as developer reputation, where we try to make decisions about, not only is the program trustworthy or not trustworthy, but is the developer backing up that program trustworthy or not trustworthy? Stack analysis, dynamic analysis, reputation, that kind of thing. The other things we do are things like Chrome safe browsing. Again, the goal is to build sort of layers of defense, concentric rings of defense. And so if Chrome believes that you're about to visit badness, whether it's badness through an APK, badness through a phishing site, badness through something else, Chrome makes sure we warn you. And again, try to keep you away from it. We have things like Safety Net. We actually have Safety Net as our way to measure the health of the ecosystem. I really like to think of security vulnerabilities like the medical industry thinks about diseases, something we're trying to prevent. And what we do is we try to measure the level of exploitation that we see in the ecosystem. We try to measure what the health of the ecosystem is. And we try to collect a lot of really good information and statistics about the safety of the ecosystem. If you want to learn more, I listed some links up here. Source.android.com/security is our primary landing spot for technical security information. Just a few months ago, we published the Android Security Year in Review. And so it gives sort of our perspective on the security state of the ecosystem, what we see, where we see the ecosystem going, what we see happening in the ecosystem. And if you have an opportunity to, I would really encourage you to review the Android Security State of the Union. It was the 2015 Black Hat presentation, where we really talked about the security of the ecosystem and what we're doing sort of overall. The information is a year old, but for the most part, it's still accurate. And so I really encourage you to review it. So now we're going to jump into really the area that I love, the area that I'm excited about, the Android platform. Android was originally built from the ground up with security in mind. Initially, we focused on application sandboxes. So the area at the top that's labeled user 1, user 2, games, contact, that kind of thing. I apologize. I'll try to point on both screens. The focus early on was on making sure that applications were compartmentalized from other applications, that application developers could have control over the integrity of their data, the confidentiality of their data, and that we protected the application data. And the way we did this was through what are called UID sandboxes. What we did was, for those of you who are familiar with multi-user Linux systems, every Linux user logs into the device. One Linux user can't access the files, the process, other data associated with other users. And so we reused that model because it was a time-proven model. And we said, let's go ahead and apply that to applications. So each application runs in its own dedicated UID space. And so this was great. This gave application isolation. It gave the ability for developers to really control the integrity and the confidentiality of their data. And then we started growing from there. So the next major addition that we made was to start splitting up Android into multiple different physical users. So we refer to the phrase the meat users, the person who's actually using the tablet. So we started introducing segmentation and separation between different physical users on the same Android device. Again, with the goal of having isolation and compartmentalization throughout Android. In Android 5.0, we switched to SE Linux fully enforcing mode. And one of the great things that did was that actually created sandboxes, not only around the applications where we focused a lot of our initial efforts, but also on every component that runs on Android, every root component, every system component. One of the things that a lot of people don't realize is that starting as Android 5.0, there is no user space concept of an all-powerful root user. The root user has SE Linux constraints and controls. Sorry, every individual program on Android, down to the small shell script, has an SE Linux policy around it that really dictates the minimal properties of what we expect. So people talk about, I rooted my Android device. Root as a concept does not exist in any daemon that we have. To get the same level of compromise on a post 5.0 device, you really have to target the kernel, where the kernel does the security enforcement. But the idea is, what we've been doing is really focusing, so security engineers and security designers, their job is to draw boxes around things and say, this is one compartment, this is another compartment. And so what we've been doing is building up Android over time, getting tighter and tighter compartmentalization for every component that runs in Android. We also, we recognize that there are vulnerabilities against the kernel. And so an area that we an area that we've been focusing on are things like trust zone the hardware for sensitive data where even a kernel compromise could be problematic. We have capabilities to put crypto keys, fingerprints, other things into the hardware, into trust zone, to try to protect the most sensitive data. Again, this is all focused on maintaining the integrity and confidentiality of application data. We take a very classic approach to information security. I don't know how many people here are familiar with the AIC model, the accessibility, integrity, and confidentiality model. So we're big believers in it, and we do a number of things to protect against that. Exploit mitigation, things like ASLR, NX. We're one of the first operating systems to basically ban non-pi binaries. And we said, hey, we really believe that ASLR is important. We're going to require not only all of our applications, but all of the third-party applications to use that. Exploit containment. Like I mentioned before, every process is an SE Linux sandbox. We know that bad things are going to happen. We know that the mitigations are mitigations. They're designed to buy us time. So we're going to make sure that we can reason about the state of the system, even in the presence of a compromise. Architectural decomposition, I mentioned this already. The goal of a security engineer is really to take big monolithic components and try to make them as small as possible. Attack surface reduction is one of the most valuable things that we can do as security engineers. If there's functionality which isn't needed, let's turn it off. One of the things that we did in Android N, for example, is removed access to large chunks of the /sys file system. So if you try to just crawl over the files there, you may be able to get a few files that we've opened up, but for the most part, the entire sys file system is gone in Android N. Safe by design APIs. We know that if we develop features, but they're too hard to use, people won't use it. We try to make our APIs and everything that we do as simple as possible and make it the secure way, the easy way. So these are really the philosophies that we believe in. And now we're going to talk about software flaws. Jump into like some specific vulnerabilities. People make mistakes. It's very easy to create a software bug. And so our job as security engineers is to create environments where even if somebody makes a mistake, it's not catastrophic. The first bug I wanted to talk about was something that you might have heard about from last year. It was a vulnerability called PingPong root. So how many people were here last year for the Black Hat talk have heard about this vulnerability? So this is a vulnerability. It was actually, the Keen team folks discovered it. I gave a link at the bottom of the page that talks about their Black Hat slides. I really couldn't do the level of justice that they could do to it. But it was a kernel-based vulnerability. It happened to do it because there was a failure to clear out some data structures on the ping sockets. And so the result was kernel code execution. Eventually, the device got user space, SE Linux was turned off, the user space was compromised, bad things happened. So it's interesting, I talked about software flaws, and so we started tracing back after this. Oh, I'm sorry, actually, I wanted to talk about one other thing. And so this was actually publicly disclosed. The first that we heard about it was on OSS Security. They sent a nice email saying, hey, can we get CVE for this? And so that immediately started our incident response process. So we started reviewing how did this actually happen. And it turns out that some engineer, yours truly, was trying to do security hardening. And so I was trying to get rid of set UID binaries. And I said, hey, why don't we open up these ICMP sockets so we don't have to have a set UID root ping? This is awesome because we can get rid of set UID root programs. The thing is that I didn't realize at the time, but this was opening up the security holes, making the ping sockets reachable to user space. So people make mistakes. I'm probably one of the first people up here to actually be talking about a mistake that I made that was presented at Black Hat. Maybe, maybe not. Don't know. So obviously, first priority when we see a bug, fix the bug. And that's easy. We started our incident response process. We had notification out to our partners right away. We made sure they knew what they were doing. We had our devices patched within record time. We wrote something called we wrote unit tests. We have a unit testing framework called CTS. It's our compatibility test suite. So we got testing in place for it. And so we followed the sort of standard incident response process, but that's not enough. And that's not good enough. Going back to the principles I talked about earlier, exploit mitigation, containment, attack surface reduction, safe by default, architectural decomposition, it isn't enough to just solely fix bugs. So the first thing we did was actually a recommendation that was suggested by the Keen Team folks. So Jeff, which is sitting over there somewhere, was sitting at the Keen Team presentation at Black Hat. He was watching the presentation. He has his laptop out. And so as the presentation was going on, they were talking about, well, there's this list poison value. It's actually pointing to user space. That means that if this data structure is coming from an area of region that's not in the kernel, it's coming from user space. So he's in the audience. And he starts typing up a patch for this. Let's get it fixed. So it's something I was really happy about. Within 12 days after Black Hat was done, we had a patch submitted, accepted to the upstream kernel, where not only we made our devices safer, but we made devices across the entire Linux community safer. So that was the first mitigation that we put in place. Let's get the list pointer out of user space. What are some other changes that we made? So we started reviewing and we said, well, the ICMP socket, that family, we're going to need to continue to make sure that it's accessible because it's needed for legitimate functionality. But are there other socket families that we can go after? And we don't have to expose them to user space. So for the most part, we were already disallowing things like netlink sockets, ton sockets, a lot of the other socket classes that you see up on this sort of never allow rule. But one of the things we realized is that one socket class in particular, SE Linux defines something called the generic socket class, and it's for socket classes which aren't known to SE Linux policy. It's sort of the generic name we give it. That class was still open, and that was opened up for Bluetooth sockets. And so we said, well, why is this open? Is anybody using it? So we put in rules. We checked to see if anybody was using it. Nobody's using it. Attack surface reduction. It's something we can eliminate. And so we went ahead and shut it down. We backported that as CVE 2016-3762, notified the entire ecosystem, our partners, the public, and made sure we addressed that. It actually addressed a number of bugs, not just, like for example, we've seen some vulnerabilities against the AF, MSM, IPC socket family. And so it's an area where we had already been blocking a lot of socket classes, and we finished shutting it down. The other thing that we've done over time is to really focus on ioctl whitelisting. A surprising number of bugs come from ioctls. And so one of the changes that Google contributed to the upstream SE Linux community was the ability to do filtering on an ioctl by ioctl basis. This shipped as part of Android M, where we're actually blocking access to the iOctal that gets the MAC address. And in N, we push that forward. We basically have a whitelist of every iOctal that you can have on networking sockets. So again, attack surface reduction, very low cost way, high impact way of making users safer. So I talked about limiting network socket families. I talked about the list pointer mitigation. I talked about iOctal filtering. We had one bug, and we were able to fix that one bug. We want to fix every bug. In fact, a lot of the bugs that you see in the Android security bulletins aren't even reachable to user space. We send them out anyway because in the interest of defense in depth and making sure that making sure that people can't chain vulnerabilities, you want to get them fixed. One bug, 3 mitigations. So it's something that I'm really happy about. And the mitigations have been effective. So we've already seen 3 different bugs, at least 3 different bugs. I sort of stopped counting because I was running out of time for my presentation. 3 different bugs that where the mitigations helped lower the severity of this bug. We still fixed it. We still notify partners. We still made sure it's addressed. But the severity isn't as great. And I listed them up here, the 2016, 2059 IPC router. The first 2 have to do with the MSM IPC socket family. The third one was a security vulnerability in the Nexus 5 wireless LAN driver. So the mitigations are effective. We know that they work. We know that they reduce the severity of bugs. Stagefright. How many people here have heard of Stagefright? Oh, come on. The rest of you, I think everybody in this room has heard of Stagefright. So this was a vulnerability that was discovered by Joshua Drake. He reported it privately to us. We let him know about it. We really appreciate it. It's awesome. Public disclosure came later. The first time I heard about it was NPR, National Public Radio. There was a blog post about it, PR, advertising buys. For this purpose of this presentation, I'm actually going to be focusing on one particular CVE, CVE 2015 3824. And this is called the MPEG-4 TX3G integer overflow. Stagefright to me was a very interesting bug. And it's actually, how many people are familiar with the phrase, a successful failure? No? No? How many people have watched the movie Apollo 13? Yeah. So Apollo 13, they were launching a spacecraft to the moon. And they stirred the cryogenic tanks, and boom, things exploded. They needed to figure out how to get the astronauts home safely. There was a consumable problem. And they did it. They got them home safely. It was one of NASA's finest hours. And in the same way, I consider Stagefright to be one of Android security's finest hours. So it led to a lot of different things. We had our monthly patching cycle. So this month is actually going to be the 12th month where we've been patching Nexus devices, making sure that all these devices are updated on a monthly basis, something I'm very proud of. It introduced the public security bulletins. So we had been notifying partners about the security issues. And we said, well, you know, let's go ahead and do it. The public security bulletins I mentioned, you know, they have a lot of bugs in there. A lot of them aren't reachable. I actually have this nice quote from JDuck. Every time I look at the changes in these bulletins, I get sad because a lot of the time these bugs are useless for attackers. I just want to make sure I mention that. No evidence of malicious exploitation. Now, our visibility may not be great, but nobody in the ecosystem has found anybody exploiting this on a malicious basis. I mean, we see isolated attacks here and there. The mitigations and the mitigations actually bought time. And they did exactly what they were intended to do. They bought us time to deploy the patches, make sure people were fixed. The device diversity also helped substantially. Nobody's ever performed an attack at such large scale where there's so many different devices. It frustrates an attacker, complicates the testing process for vulnerability. The exploit containment worked, and I'm going to talk more about that later on. It forced vulnerability chaining. The patch itself is widely distributed. According to Zimperium, the Stagefright patches are on anywhere from 57 to 89% of the 1.5 or 1.75 billion devices that are on the internet. So amazing, amazing solid patch penetration. Significant architectural improvements, I'm going to talk about that later. And enhanced visibility of the Android Rewards program. We pay up to $50,000 if you can produce the right kind of exploit with the right kind of test, with a patch available. And we want to pay for vulnerabilities, and we want Android to be as safe as possible. So we've got significant traction on the Android Vulnerability Rewards program. So let's talk a little bit about patching. I mentioned the Zimperium numbers for where we're at. But this last year has actually brought huge improvements at the rate at which updates are actually being delivered to users' devices. To really give you a sense of where we're at, you can take a look at this table. And this table shows 22 devices across 22 flagship devices across the 4 major manufacturers over the last 3 months, and whether they have security patches or not. So this is based on real data that's coming in from SafetyNet and from some of our telemetry. And you can see that the vast majority of devices are within a 30-day patch window. Even greater percentage are within 60 days, and all of them are basically within a 90-day patch window. So we've made tremendous progress addressing patching throughout the ecosystem. And Samsung in particular is really noteworthy. They've been providing updates for all of their flagship models for the last 3 months. LG's been making significant progress. But to be balanced, there are actually lots of different Android devices, and most Android devices are still not getting updates. And so we're continuing to work with our OEM partners and carrier partners to make sure that updates are reaching an increasing number of devices at a faster and faster cadence. I mentioned containment. Stagefright was, the media server was designed for containment. And we actually focused on that. There was a presentation given by Rich Cannings back in 2009 at the Usenix Security Conference, where we talked about how we understood at that time that parsing media codecs was dangerous. And so we created a sandbox at that time. It was actually it was first effective in the vulnerability that Charlie Miller discovered, OSearch 2009-002. It was an MPEG-4 parsing vulnerability. And in the case of Stagefright, in the case of the bugs that were reported, they were contained. The vulnerability required, the exploit was contained. We were able to reason about what would happen to the device in the presence of a compromise. JDuck posted this on Twitter. He was showing how his exploit works, and he said, however, media server is limited by both its privileges, which are pretty high, and the SE-Linux policy. And we can't even read the shell script interpreter. So now, media server grew up, it developed more features, and so I think there was a fair point that we had to revisit the containment that was happening on the device for Stagefright. So first priority, fix the bug. The bug fix was pretty simple. If size is less than chunk size, return malformed. Thing to keep in mind here is that chunk size is a 64-bit value. This will become important later. So we were fortunate that the vulnerability was reported. The vulnerability reporters looked at the patch, created the patch. I looked at the patch. Other people on the media team looked at the patch. Nobody saw any problem with it. Awesome. Except it wasn't awesome. So it turns out that there was a bug in the patch. And I mentioned that chunk size was a 64-bit value. And it turns out that if you do the arithmetic operation, it's actually doing it as a 32-bit value. So you still end up with an int or underflow. So that led to CVE 2015-3864, which was to get the patch properly fixed. I reviewed this, a vulnerability reporter reviewed this. Humans make mistakes in the efforts in creating software. and it's up to security professionals to help put seatbelts on and make sure these environments are safer. Solely fixing bugs is acceptable. I mentioned that earlier. So we did a number of changes to make Android more secure. I want to talk about media server refactoring, Android overflow protections, ASLR. These are all things that we did. I'm going to talk about each one of these. So the first thing we did was, I talked about the principle of architectural decomposition, trying to take big things and turn them into little things. This is how we make the, systems more secure. And so we looked at the containment model for media server. And we said, are there changes that we can do to make it better? So the first thing we did was we actually we had one process called media server, and it had a number of different services in there. And so what we did was we split it into 6 processes, 6 servers. And you can sort of see the breakdown here. You have media DRM server, media codec server, extractor server. And this was actually really nice because what it allowed us to do is, where media server before had a whole set of permissions, the ability to access the GPU, the ability to make network sockets, we are able to partition those permissions across all the other ones. Now, a lot of the Stagefright vulnerabilities occurred in the media media extractor service, down in the very lower right-hand corner. And one of the things you'll see there is that that doesn't have any permissions. It's one of the tightest sandboxes today on Android. And so we know if a vulnerability was to happen like Stagefright, we could reason about it and make sure that the extractor service is appropriately contained. So the media server refactoring was a huge improvement for Android security. Vastly improved architectural decomposition, vastly improved separation of privileges. The most dangerous code was moved to the most isolated process where we could reason about it and contain it. And the containment model was significantly more robust. Everybody's safer. The other thing we found was integer overflows. So I'm sure everybody here is familiar with computer math. You keep adding to a certain value and eventually it wraps around. This is something that only computer science folks seem to accept. If you're to tell a mathematician, hey, if you take a number and you add 1 to it, you'll end up with a number that's less than it, they're going to tell you you're crazy. But somehow this has been accepted within the computer science community for decades. In C and C++, you add values. If you have a signed value, it's undefined if it wraps around. If you have unsigned value, it takes the value modulo 2. This is defined, but it's also defined to be counterintuitive. That's not the expectation that most people have is that numbers don't get smaller if you add to it. So all the vulnerabilities a big chunk of the vulnerabilities that we saw were unsigned integer overflows. We said, what can we do to make it better? UBSAN. UBSAN is the undefined behavior sanitizer that's built into Clang. And we said, we can fix this. So we turned on integer overflow protection across Android. And what did that do? So here was the original code, here was the original assembly. Before UBSAN was turned on, you can see there was an arithmetic operation. The arithmetic operation didn't have a checking. You allocated a too small of a region, then you mem-copied into that too small of a region. Memory corruption happens, bad things happen, world goes boom. We turned on integer overflow sanitization. What does integer overflow sanitization do? It actually, if there's a wraparound on an integer value, it calls abort. So it adds safety belts and seat belts to every arithmetic operation. So in this case, we had our original vulnerability, but we turned on integer sanitization. So there was some assembly that was added here. It's a 64-bit assembly, so you have to do that as 2 32-bit operations. The essence of this code basically is that if the number gets too big, if the number wraps around, call abort. So this would have been sufficient to catch the vulnerability. And in addition, it would have been sufficient to catch the vulnerability even in the presence of our initial malformed patch. So you can see we added a check there. We said, oh, if the 32-bit addition wraps around, if the 32-bit value doesn't make any sense, go ahead and return error malformed. And then the compiler backed us up and said, okay, I'm going to add the check and make sure that you actually mean what you say you mean. So UBSAN is amazing. Without the patch, it would have stopped the bug. With the bad patch, it would have stopped the bug. Obviously, we want the correct patch because then it's still a denial of service, but that's the goal, to turn security bugs into just plain bugs. And I encourage you to read this link. It's our Hardening the Media Stack post where we go into a lot more detail. ASLR. ASLR is something that a lot of people really care about, and it was really effective in the early stages of the Stagefright vulnerability. So we said, after this happened, are there things that we can do to make ASLR better? So randomize all the things. First thing we did was we recognized 8 bits of randomness isn't really enough. It's good for remote attacks, but even when the ASLR was created, it was recognized that 8 bits of entropy isn't really that much. The Project Zero folks outlined the Stagefright exploit, and they believed that they could exploit it in just about under 10 minutes. So we said, let's increase it to 16 bits. Let's increase the base mmap randomization to 16 bits. And so the same vulnerability, had it occurred, statistically, we expect it would have taken about 45 hours to perform the exploit versus 10 minutes. Significant improvement. We sent this upstream. The entire Linux community is safer as a result of the changes we made. But let's randomize more. The second change that we made is focused on what I call library load order randomization. Normally, when you load libraries, you load them sequentially. But we realized that libraries don't need to be loaded sequentially. They can be loaded out of order. So rather than going 1, 2, 3, 4, let's do 2, 3, 1, 4 this time, and 1, 3, 2, 4 the next time. It adds a little bit more entropy. It builds on top of the mmap-based randomization that we already have. And so it makes things a little bit safer for the executable code segments. It doesn't do anything to address malloc to memory or things like that. It also doesn't do anything to address the linker, the base linker, or the Pi executable. But I think it's a solid improvement. This was a late change to the slides, where this was just checked in, 15 days ago. So it's not going to be part of Android N, but probably the next version of Android. Could be O, could be N+1, I don't know what it is. We actually started inserting random gaps in between shared libraries. This was primarily done to support future CFI work that we're working on, but it also has the advantage that there's now gaps between shared libraries and sort of more randomization. So it's harder for an attacker to find a region of executable to jump to. There's been a bunch of other changes. Prior to, in Android M, the media server was allowed something called execmem. This was the ability to create anonymous executable memory. So if you look at the right-hand side, you'll see a call to mmap2 with map anonymous. Before, this would actually return. So what attackers would do is they would get enough of a ROP chain in order to sort of set up their initial payload. They would load their payload into memory, map is executable, and then jump to the shellcode. That's no longer possible in Android N. So right now in media server, the only way you can get executable code loaded into memory is it must come from a verified partition. This was partially true back in the Android M stage 2. Like, we don't allow media server to load executable code from the data partition. But this is now more true today. You literally cannot map anything into memory executable unless it has come from a verified partition. Signature checked, verified, DM Verity protected partition. In addition, we have setcomp enforcement for the media server process. Only a whitelist of system calls are allowed to be executed. So if you try, for example, executing FNet module, well, that's shut down. We'll just kill the process on invalid system call. So we've had the restriction on loading executable code from data to data in place for a while. This just makes it more solid and more protected. So we saw a bug. There was lots of postmortems. There was lots of things that happened. And when we got around to it, we spent time really putting in place 7 solid mitigations that not only protect the media server process, but a lot of the mitigations protect Android as a whole. And so significant improvements that we've made. I wanted to talk about data and transit protection. So Everybody in this room knows that the network is not to be trusted. This has always been true, especially for mobile devices. So you carry around some of the most confidential information on your device. And there's still in this world too much unencrypted traffic. So I hope everybody can go back and identify what you can do to move to HTTPS. Please do that. Let's get rid of clear text completely. So in Marshmallow, we had a big focus on clear text traffic. And so we introduced two features in Marshmallow that were intended to address the problems of clear text traffic. The first one was our clear text death mode. I actually hate that phrase, but clear text death mode and strict mode, actually, death penalty strict mode. If the libraries within Android detect that you're trying to perform clear text traffic, we will go ahead and, if you've opted into it, we will go ahead and kill your application on your behalf to make sure that you just can't do that. It prevents accidental regressions in it. It's a best effort. We've instrumented various libraries around Android. There's lots of ways to work around it. It's intended to help you as a developer be more secure. Similarly, we also introduced an application manifest called Android uses clear text traffic equals false. And this is a message to other parts of Android that clear text traffic isn't, other parts of Android are not allowed to issue clear text traffic requests on your behalf. So these are not limited to HTTP. These are not limited to HTTPS. And so that was really the big focus of Android Marshmallow. In Nougat, we also recognize that there's a lot of poorly encrypted traffic. So we said, what can we do to address that? And in 2014, there was a security researcher who scanned a number of applications in market in Google Play and said, are these applications based on static code analysis doing things that would make them subject to man-in-the-middle attacks against HTTPS or TLS? And if you do if you do a MITRE search, a CVE search for Android X509, you actually find that there are about 1,400 applications where they weren't using HTTPS properly. So one of the big focuses for our data and transit team was how could we actually make this better? And what could we do to improve the situation? First thing we had to do was understand, why are these bugs happening? One of the most common reasons that we found was, so if you have a development environment, you're testing out your application, well, you need to be able to connect to a server that you control. And you need to be, and that server hopefully doesn't have your company's private certificate. So you might create a certificate on your own local machine, and you might hard code this in, or you might temporarily disable HTTPS because you're trying to test out your application. You're trying to make sure it works. So we found that a lot of people were accidentally leaving in debugging code into their application. Or they just weren't thinking about removing it later. Another thing that we found was a lot of the APIs that are available in Android and other operating systems too have global state associated with them. So it's very common for an Android application developer to grab code from here, code from here, code from here, and not necessarily understand exactly not understand at a very fine-grained level exactly what that code's doing. And that's dangerous for its own case, but in the case of HTTPS, it actually opened up security holes in your application. The third-party libraries were changing global state. Insecure code samples online. Cough, Stack Overflow, cough. There's a lot of bad advice out there about what to do. And there's a lot of people that are cutting and pasting code. I think the presentation that, who gave the intro presentation for Black Hat? He talked about this. We as an ecosystem, we as an industry don't actually share the proper ways to do this. We rely on places like Stack Overflow to do it, and a lot of times they're wrong. We also see vulnerabilities that occur due to connections to legacy servers. I wanted to list out a few samples of code that we've seen. For the love of God, please do not put any of these into your application at all. A developer might want to say, well, I have this default hostname verifier, and that makes sure that when I'm making a request, I'm actually connecting to www.mycompany.com instead of www.evil.com. The problem is when you're in a development environment, you might need to be connecting to your desktop machine, which has a slightly different host name. So people have put this in their code. We'll honor the certificate, but we just won't actually check the name on the certificate itself. So we return true all the time to verify. It seems to work good in development. It seems to work good in production. Everything's great. It's broken. Another example was really focused around checking to see if a client was trusted. Checking to see if a server was trusted. Now, the contract with these APIs is that they throw an exception if something is bad. Well, for development, you might not want to do that. And so you don't throw the exception. Again, it looks like everything's working, but it's not working how you intended. So we introduced the network security config. We recognized that the existing APIs were too prone. I talked about safe by default. We're trying to make things safe by default. It's an easier API to use to configure TLS traffic. It allows you fine-grained control over insecure or secure traffic. It has special provisions for debuggability within your code. So you can add special rules that the operating system will enforce that we remove it at build time. It allows you to really limit the CAs that you want to trust. And it provides a really easy mechanism for doing pinning of your application. So we think it's a good, solid improvement. Try to remove the really complicated code, make it a static configuration file that defines how your service runs. I listed a few examples here. Let's say, for example, you have a web browser, an application, and it connects to lots of different places. It could connect to your secure website, and you want to force that will always be secure. So we can enforce that. But other places, you don't mind if it's insecure. So this is the syntax that is used to say, I want to enforce that all the traffic to secure.example.com and subdomains of that traffic are always forced to be secure, and we don't allow any kind of clear text traffic. Very simple, very easy to understand, no need to write any code. You might want to restrict which CAs you trust. Perhaps you don't trust a certificate from a random country. And so you could actually embed that within your application and say, I only want to trust these certificates. And so you can define that. Lots of control, lots of power, very simple syntax. Or you can even do pinning. And so again, you could embed a hash of your certificate into your application itself. And that way, if the Android network stack tries to connect to something that's not allowed, it will be rejected. The expiration date is very. During the course of writing the network security config, we had the opportunity to revisit how we thought about large chunks of how we do certificate management. And so one of the things we did was we reevaluated how we should handle user-installed certs. And so by default, Android files and process and other data is protected from other applications, is protected from the user. But that same rule wasn't true for network traffic. And so we said there's an inconsistency here. We also started seeing interest from nation states. So you guys might have read about this back in 2015. Kazakhstan's considering requiring all of their citizens to install a certificate on their device. Concerning. So we said, well, let's revisit how we think about this. Most application developers weren't actually aware that their secure traffic could be intercepted by a library on Android. And we also found that just user-installed certificates were not really commonly used. So one of the changes that we made for N was to have consistency with the file model and the process model, and actually say that user-installed applications which target NuGet or above no longer trust user-installed certs by default. We empower application developers to make that choice, whether they want to trust it or not. But NuGet applications or above no longer honor user-installed certs. Where do we go from here? We only have a couple minutes left. So I talked a lot about safe by design, architectures, that kind of thing. We as an industry need to move away from memory unsafe languages. Something like 85.9% of the security bugs that we deal with in Android have to do with native code vulnerabilities. Android was a great Android really has encouraged the use of Java for applications. It's been one of the things that saved us over and over again. Applications are very secure because they use Java. We need to get more memory safety within these platforms. And that's true for even critical infrastructure, things like the Linux kernel. We need to figure out a way to make this happen. I don't know how to do it, but we need to figure it out. And we also really need to invest in defenses. So exploit mitigation, exploit containment, CFI. We need to invest in mitigations and make sure that we're honoring these principles that are up here, and that we are protecting our users and making the entire ecosystem safer. So, Black Hat sound bites. We have a really robust multi-layered defense. It's designed to mitigate and contain vulnerabilities. It's something I'm very proud of. We are really heavily investing in learning from vulnerabilities and trying to figure out how we can make things better. And we know that vulnerabilities will never go away, but they can be managed, they can be contained, people can be kept safe even in the presence of vulnerabilities. So I want to say thank you.